Now continuing from the previous question where we left, in this question we have to find out the distance x at which we should keep this mass m so that net force acting on this mass is 0. So let us suppose that the distance of this mass m is x from this to m. So first of all we have to find out the simplest ratio. We are doing this question by that trick which I have demonstrated in the previous video. So first of all we have to find out the simplest ratio, which is 2m is to 18m, that is 1:9, and then we have to find out the root of the ratio, root of simplest ratio. So this root will be equal to 1:3. Now we have to add up this ratio 1:3, and this will be 4, and one part will be r upon 4. Now as we know that after taking the square root of the simplest ratio, the part of this 2m is 1, so the distance x is measured from 2m. So we can say that x would be equal to 1 part and this y would be equal to 3 parts. So the value of x will be r by 4 and the value of y will be 3r by 4. So at this distance, the net force acting on this mass m would be 0. In this question, you can see that there are 4 masses which are kept on the corners of a square, and the side of the square is A. Now we have to find out the net force acting on any one of the mass. So let's suppose this is the mass on which we have to find out the force, and these are the forces which are acting due to all of these 3 masses. So we all know that the value of magnitude of force F1 and F2 will be equal, and it would be equal to g m square, this is m into m, upon r a square, which is the distance between these 2 masses. So this force is, let's suppose this is F1, and this F3 will be equal to g m square, m into m, upon this distance. So this distance would be root 2a. You can see that this is root 2a, the diagonal of the square. So it is root 2a whole square. So this is g m square by 2a square. So now you can see that that this angle is 45 degree and this is 45 degree. So if we draw the free body diagram of this mass, then this is F1, this is F1, and this is F1 by 2. You can see that F1 is equal to gm square by a square and F3 is gm square by 2a square. So it is F1 by 2. So this is F1 by 2. This is 45 and this is 45. So the resultant force acting on this mass will be F1 by 2 plus twice of F1 cos 45, because this is F1 cos 45 and this is F1 cos 45, and these components F1 sin 45 and F1 sin 45 would be cancelled out. So this is twice of F1 cos 45. So resultant force will be equal to F1 is taken out, and this is 1 by 2 plus root 2, 2 by root 2. So F resultant will be equal to g m square by a square into 2 root 2 plus 1 divided by 2. So this is the resultant force acting on this mass which is kept on the corner of the square. In this question, you can see that there are 4 masses which are out of which 3 are kept on the corners of a equilateral triangle and one of them is kept at the centroid. So the side of the equilateral triangle is A, and this distance we all know that this is equal to a by root 3. You can find it out by dividing this median, which is root 3 a by 2, in 2:1 part. So this is 2 part and this is 1 part. So this is equal to a by root 3, and this distance is equal to a by 2 root 3. Now let us draw the forces which are acting on this mass. So this mass is being pulled by a force F due to this mass, this one, and another same force F will be acting on this mass due to this one, and another force F dash will be acting on this mass due to this M. So if I draw the free body diagram, then this is F and this is F, and this force is F dash. This angle is 30 and this angle is 30. So the resultant force will be equal to F dash plus 2F cos 30 again. Now the value of F is g m square by a square, while the value of F dash will be g m square by a by root 3 whole square. So F dash will be equal to 3 gm square by a square and therefore F dash can be written as thrice of F. So this F resultant will be equal to thrice of F plus 2F into cos 30 is root 3 by 2. So F resultant will be equal to root 3. F is common, 1 plus root 3. Okay, and the value of F is this one. So resultant force will be root 3 gm square by a square into 1 plus root 3. This is the value of resultant force acting on this mass M. In this question, you can see that there are three masses, equal masses M, M and M. They are rotating in a circle about their common center, which is the centroid of this triangle. So they are always rotating in this circle in such a way such that they always form a triangle, equilateral triangle. And we have to find out this omega, which is the angular velocity of all of them. So we know that they are rotating in this circle due to their mutual gravitational force. And if we assume that this triangle has a side of A, then this R will be equal to A by 2 root 3. In fact, A by root 3. Because we know that if this side is A, then this distance is A by root 3. So we can write this R as A by root 3. But in question, we are given with R, but not with A. So we can find out the value of A as root 3R. Okay. Now we can see that the force acting on any one of the mass is this F and this is F. And let's suppose that the pseudo force acting on it is this one. This is M R omega square. So this angle is 30 and this is 30. So the component of F along this line is F cos 30 and F cos 30. So 2F cos 30 is actually balancing M R omega square, where 2 and F is equal to, this F will be the force acting on this mass due to this one. So F will be G M square upon A square. So F is G M square upon A square, and cos 30 is root 3 by 2. And this is equal to M R omega square. So let me remind you that we are not given as we are not given with A, we are given with R. So we have to eliminate A. So I'm cancelling out this 2 with 2 and this M with M. So Gm by A square, which is 3R square into root 3 is equal to R omega square. And therefore omega will be equal to under root of Gm by root 3 R cube. So you can see that this is the common angular velocity with which these are rotating about their centroid as a center of the circle. In this problem, you can see that there are 4 masses which are placed on the corners of a square, and the radius of this circle in which they are rotating is R. The center of the square is the same as the center of the circle, and they are rotating under the influence of their mutual gravity. Now we have to find out the omega, which is the angular velocity of rotation of them. So first of all, let us concentrate on any one of the mass. So let us find out the net force acting on this mass. So if we write down the total gravitational force, then this is F, this one is F, and the force which is applied by the diagonally opposite mass is also, let's suppose it is F dash. And these forces are balancing this pseudo force which is mr omega square. Now first of all, let us assume that the side of the square is A, and we know that the diagonal of the square is root 2A. So root 2A is equal to 2R. You can see that this is 2R and this is root 2A. So A will be equal to root 2R. So first of all, this is the side of the square. Now the value of force which is applied by this mass on this mass is Gm square upon A square, because the distance between them is A and the masses are equal. Now the value of F dash will be Gm square by, this is root 2A, and therefore it is root 2A whole square. So F dash will be equal to Gm square by 2A square, and this is F by 2. Okay, so now if we write down the net force, then this is F, and this is F, and this is F by 2, and this angle is 45 degree obviously, because diagonal of the square divides this complete angle into 2 equal parts. Now a force of m r omega square is acting in just opposite direction, and the resultant of all these 3 forces is balancing this mr omega square. So the resultant would be F by 2 plus 2F cos 45, and this is balancing mr omega square. Now you can see that this is F by 2 and plus cos 45 is 1 by root 2. So it is root 2F, and this is mr omega square. So F, I am taking F as common. So this is Gm square by this is Gm square by A square, and 1 by 2 plus root 2 that is equal to mr, where r is equal to, this is r omega square, and the value of A is root 2r. So this is I'm writing it here, that Gm square by 2r square, and this is 2, and 2 root 2 plus 1 is equal to mr omega square. So cancelling this m with m, omega will be equal to under root of Gm 2 root 2 plus 1 upon, this is 4r cube. So this is the value of omega, which is the angular velocity with which this system is rotating about the center. In this question, there is a rod of mass m and length L, and there is a mass m which is a point mass, and the value of this mass is same as that of the mass of the rod. It is placed at a distance of L from this end of the rod, and we have to find out the gravitational force acting on this mass by the rod. So we must notice a very important thing, that the Newton's law of gravitation is only valid for point masses, but this is an extended mass, so we cannot apply directly the Newton's law of motion in this rod. So we have to assume an element which is so small so that it may behave like a point mass, and therefore the width of this element is dx and the distance of this element from this point is x. So let us suppose that the mass of this element is dm, and dm will be equal to m by L into dx. Okay, so the gravitational force acting on this mass due to this element would be g m into dm divided by x square, gm1 m2 by x square, and the value of dm is m by L into dx. The total force F will be the integration of df, and therefore this is integration of g m square by x square, and this is L and this is dx. So this will be g m square by L integration dx by x square. The limit of x would be from this end to this end, and at this end x is equal to L, and at this end x is equal to 2L. So the limit of x would be from L to 2L, and therefore it is f will be equal to g m square by L, and the integration of 1 upon x square is minus 1 upon x. So it is minus 1 upon x, and the limit would be from L to 2L. So f will be equal to g m square by L, and let us take this minus common, and this is 1 by 2L minus 1 by L. So f will be equal to plus g m square by 2L square. This is the force acting on this mass due to this rod. So this is the net force.